Welcome back to Neural Intel. Today we're doing another deep dive, this time into a really fascinating corner of AI research.
That's right. We're looking at how to make these huge AI models, the really powerful ones, much more adaptable.
Exactly. More efficient when they have to learn in environments that are constantly changing. We've got some great sources here covering continual learning CL and also a set of techniques called parameter efficient fine-tuning, or PEFT.
And our mission today really is to unpack how these two areas are kind of converging, how they're working together to build what might be the next generation of AI models.
Right. And as always here on Neural Intel, we'll be focusing squarely on the technical details, the research itself, and the implications for the technology. For links to the research papers we discuss, definitely check out our webpage links in the bio.
Yeah, so the core challenge we're trying to get our heads around is this. You have these massive AI models, incredibly capable, but how do you get them to keep learning? Learning new data, new tasks.
Without forgetting everything they already know. That whole catastrophic forgetting problem.
Precisely. That's a huge hurdle. And crucially, how do you do it efficiently without needing, a data center's worth of power every time you want to teach it something new?
Yeah, that efficiency part is key. So these researchers, they're looking at ways to make really small, but strategically smart changes to these models.
Exactly. Small tweaks that let them adapt as things change without the massive overhead or the forgetting.
Okay, makes sense. So let's start with that first piece, continual learning, CL. What's the fundamental idea there?
Well, at its core, CL is all about getting AI models to learn sequentially, to pick up and retain knowledge across a series of tasks over time. A bit like how humans learn throughout life, ideally.
Right, because traditional machine learning, it usually assumes the data is static, right? You train it once on a big batch.
Yeah, exactly. That's the old way. But the real world isn't static. Data flows, things change, new information comes in constantly. Yeah. That static assumption just doesn't hold up.
And that brings us back to catastrophic forgetting, the big downside of just naively training on new stuff.
It really is the central problem in CL. You teach the model task B, and its performance on task A, which it might have mastered before, just plummets.
Like wiping the slate clean, almost?
Pretty much. And there's a related issue called representation drift. Even if it doesn't totally forget, the way the model understands concepts can shift, and that shift negatively impacts its ability on older tasks.
Okay, so CL research is trying to find a balance then.
Exactly. It's this constant tension between plasticity, the ability to adapt and learn new information, and stability, the need to hold on to the knowledge it already has. Finding that sweet spot is the goal.
Makes sense. Now, the sources lay out a few different CL scenarios. These aren't all the same challenge, are they?
No, not at all. These scenarios help define the specific problem we're trying to solve. For instance, there's task incremental learning, or TIL.
TL.
In TIL, the model learns completely distinct tasks, one after another. Think different sets of labels or categories. And importantly, when it's tested, it knows which task it's supposed to be doing.
Okay, so it has that context. What else?
Then there's class incremental learning, CIL. This one's quite a bit harder. The training looks similar, new classes come in sequentially, but during the test phase, the model doesn't get told which task the data belongs to.
Ah, so it has to figure out, is this from task A, B, or C, and classify it correctly across everything it's ever seen?
Exactly. Much more challenging. Then you have domain incremental learning, DIL. Here, the classes, the categories themselves, stay the same, but the data distribution changes.
Like recognizing cats in photos, then recognizing cats in sketches, then in infrared.
Perfect example. Same underlying task, different data domains. And again, no task ID at test time.
Got it. And there are a couple more mentioned.
Yeah, online continual learning, OCL. This tries to mimic a real-time data stream. The model sees data, learns from it, and then that specific data point is discarded. It's single-pass learning, basically. Very constrained.
Wow, okay. That sounds tough.
It is. And then there are scenarios trying to be even more realistic. Class incremental with repetition, CIR, allows both new classes and the reappearance of old classes within the stream.
So it has to handle novelty and reinforcement.
Right. And finally, rainbow memory, RM. This one tackles situations where task boundaries are kind of blurry, maybe tasks share some classes. RM uses some clever memory management and data augmentation tricks based on how uncertain the model is.
Okay, that gives us a really solid picture of the different facets of the continual learning challenge. Let's switch gears now to the models themselves. These large pre-trained models, PTMs, BERT, GPT-3, vision transformers, they're everywhere. Why are they so central to this discussion?
Well, these PTMs are just enormous neural networks. They've been pre-trained on absolutely massive data sets like huge chunks of the internet for language models or vast image libraries for vision models.
And through that pre-training, they learn really general, powerful ways of representing information.
Exactly, often using architectures like the transformer with its self-attention mechanism. They learn these incredibly rich general-purpose representations. Think of BERT's understanding of language nuances or a vision transformer's ability to recognize complex patterns in images.
And the key benefit is you can take this general knowledge and adapt it, right, for more specific jobs.
Precisely, that's the standard approach. Fine-tuning. You take a PTM and you update its parameters using a smaller data set specific to your downstream task, maybe classifying sentiment or identifying specific objects.
And here's the catch. Fine-tuning these entire massive models every single time you have a new task.
Yeah.
That sounds computationally brutal.
Oh, it absolutely is. But full fine-tuning requires immense computational resources. GPUs, TPUs, lots of time, lots of energy. It's expensive.
And potentially problematic beyond cost.
Yes. If your new task dataset is small, you risk overfitting, the model gets too specialized and doesn't generalize. And crucially for our discussion, full fine-tuning is highly susceptible to that catastrophic forgetting we talked about earlier.
Right. Wiping out previous knowledge. Okay, so this is where parameter-efficient fine-tuning, PEFT, comes into play. The name kind of gives it away, but what's the core idea?
The core idea is simple but powerful. Achieve the same, or sometimes even better performance, as full fine-tuning, but by only modifying a very, very small fraction of the model's parameters.
Keeping most of that huge pre-trained network frozen.
Exactly. You freeze the vast majority of the weights and only train a small number of new or existing parameters. This drastically cuts down on compute, memory usage, and storage costs.
Okay, so how do they do that? The research breaks PFT down into, three main categories? Let's start with additive methods, adding new bits.
Yeah, that's the gist. Additive methods introduce new, typically small, task-specific parameters or modules into the pre-trained model. The original giant network stays locked. Think of it like adding a specialized tool to your toolkit without rebuilding the whole thing.
Makes sense. And the first type mentioned is adapter-based. Adapters seem to be popping up everywhere. How do they work here?
So the classic adapter approach involves inserting these small neural network modules inside the layers of the base model, often within the transformer blocks.
Little plugins, almost.
Kind of, yeah. They usually have this bottleneck structure. They squeeze the information down, process it, then expand it back up. This forces them to learn a compact, efficient representation for the new task. Only these tiny adapters are trained.
While the main model layers are untouched.
Right. And there are variations, like adaptformer for vision, adapter fusion to combine adapters, mirror for efficient integration, Atomix using multiple parallel adapters. Lots of different ways to design and use them.
Okay, adding small modules. What's the next additive approach? Prompt-based. This sounds different.
It is quite different conceptually. Instead of adding modules inside the model, prompt-based methods work at the input level. They train what are called soft prompts.
Not like the text prompts we give ChatGPT.
No, not human language prompts.
Yeah.
These are continuous vectors, basically blocks of numbers that get prepended or inserted into the input data sequence fed to the model.
And these numbers are trainable.
Exactly. The idea is that these learned vectors act as instructions, guiding the frozen pre-trained model to perform the specific downstream task correctly without actually changing any of the model's internal weights.
That's clever, like finding the magic sequence of numbers to unlock a specific skill in the model.
That's a good way to put it. Prompt tuning just learns these continuous prompts. P-tuning mixes continuous and some discrete prompts with an encoder. Prefix tuning adds trainable vectors at the start of each layer. And multitask prompt tuning tries to learn one general prompt that works for multiple tasks.
Fascinating. Okay, that covers additive methods. The second big PEFT category is reparameterization methods. Sounds a bit more complex.
It's more about changing how the existing parameters are represented or updated. The most famous example here is probably Laurel low-rank adaptation.
LoRa, right. Heard a lot about that one.
So LoRa doesn't directly change the big weight matrices in the model. Instead, for each matrix you want to adapt, it adds two much smaller low-rank matrices. The change to the original weights is represented by the product of these two small matrices.
So the update itself is low rank, meaning it doesn't capture overly complex perhaps noisy details.
Kind of. The key is that these low-rank matrices have far, far fewer parameters than the original matrix. So you train only these small matrices, very few trainable parameters, and a neat bonus. After training, you can actually merge these changes back into the original weights, so there's zero extra latency during inference.
Oh, that's a big advantage. No slowdown at runtime.
Huge advantage. And there are variants like QLRI, which adds quantization for even more memory savings. Dora focuses on decomposing weights into magnitude and direction and applying LoRa to the direction part. ROA combines low-rank and sparse adapters. VEER uses shared random matrices with learnable scaling vectors. It's an active area.
Really elegant ways to constrain the updates.
Yep.
Okay, the third category, selective methods, picking and choosing.
Exactly. Instead of adding parameters or reparameterizing updates, selective methods identify a small subset of the original model parameters and fine-tune only those, keeping everything else frozen.
How do they choose which ones?
One way is through masking. You learn a binary mask, like a stencil, that determines which weights are important for a task and should be updated. The others stay fixed.
And the other example?
PEFT. This one's pretty extreme. It proposes fine-tuning only the bias terms in the network.
Just the biases. Isn't that a tiny fraction of the parameters?
A minuscule fraction. But surprisingly, for some tasks and models, just updating the biases can yield decent adaptation performance. It's incredibly parameter efficient, though maybe not always the highest performing.
Wow. Okay, so we have CL dealing with the sequence of tasks and forgetting, and PEFT dealing with efficient adaptation. The really exciting part then is putting them together. PECFT, parameter efficient continual fine-tuning.
Yes. This convergence, PECFT, is where things get really interesting for building AI systems that can learn continuously and practically in the real world. It combines the strengths of both fields.
So what are the main advantages you get when you bring CL and PEFT together like this?
Several big ones. First, efficient task adaptation. You inherit that leanness from PE. Second, significantly mitigating catastrophic forgetting, because most of the model's core knowledge, the frozen part, is preserved.
Which is the main goal of CL anyway.
Right. Third, it makes multitask learning much more scalable. You can potentially have one base model learn dozens or hundreds of tasks just by adding or tuning a tiny number of parameters for each, instead of needing a whole separate model copy.
That's huge for deployment.
Definitely. And fourth, it makes continual learning feasible in resource-constrained settings. Think edge devices, maybe smaller research labs where full fine-tuning or older CL methods would be impossible.
Makes total sense. So let's look at some examples from the research. How are these specific PEFT methods being adapted for continual learning? Let's start with adapter-based PECFT.
Okay, so researchers are extending adapters for CL. There's CADA, which has an expandable adapter layer. ACL uses a shared feature adapter plus task-specific heads. Some methods use mixture of experts routing.
So the model learns which adapter is best for the current input.
Kinda, yeah. Dynamically routing to specialized adapters. SEMA uses an expandable router. CS is specifically for continual aspect sentiment classification. APART tackles tricky long-tailed CIL problems. ATLA combines adapter info based on similarity. And there's an expand and merge framework too. Lots of different strategies for managing adapters over time.
Very cool. What about LoRa-based PECFT? How does LoRa fit into the continual learning picture?
LoRa's efficiency makes it really attractive for CL. We see methods like Inflora, which confines updates to subspaces to avoid interference. Pelora uses orthogonal LoRa subspaces, great for federated learning. Dual LoRa uses two kinds of LoRa adapters.
Orthogonal and residual, why two?
The idea is one captures task-specific stuff cleanly, orthogonal, while the other handles shared knowledge or refinements, residual. EI LoRa mixes replay with LoRa for dialogue. Task arithmetic involves training separate LoRa's and then adding or averaging their weights. Stamina adapts LoRa for continual learning in fusion models.
The image generation models.
Yeah. And interpolation-based LoRa uses memory and mode connectivity ideas. Again, lots of variations on the core LoRa concept, tailored for CL challenges like forgetting.
It's really impressive how these core PEFT ideas are being tailored. What about prompt-based PECFT? How do prompts handle learning over time?
Prompting for CL focuses on learning sequences of these soft prompts. L2P uses a prompt pool and learns to select the right one. Dual prompt uses general prompts for shared knowledge and expert prompts for specific tasks.
So different prompts for different needs.
Right. LGCL uses language guidance to help learn better prompts. PGP integrates anti-forgetting directly into prompt tuning. S-prompts just creates a new prompt for each new domain in DIL. Coda prompt uses composite prompts with attention for adjustable capacity. Progressive prompts concatenates prompts from previous tasks. And POP uses two sets of prompts, one for telling tasks apart, one for integrating knowledge.
So many creative ways to use prompts for this. It's clear PECFT is a really vibrant research area. Now, evaluation. You mentioned it's not just about accuracy on the new task. How do they measure success?
Yeah, you absolutely need more than just final task accuracy. Average accuracy across all learned tasks is key. But just as critical is average impetuous. Forgetting how much did performance drop on old tasks when learning new ones. Lower forgetting is better, obviously.
Makes sense. What else?
Forward transfer, FWT, is interesting. Does learning task A help you learn task B faster or better? Backward transfer, BWT, is also tracked. Does learning task B actually improve performance on task A somehow, or does it hurt it?
Positive or negative interference, basically.
Exactly. And then, because efficiency is the whole point of PET, you track the number of trainable parameters, how small is the update, and often model size efficiency, which looks at how much the total model size grows as you add more tasks. Ideally, it grows very slowly.
Right, giving a full picture of the trade-offs. Okay, looking ahead, what are the big open questions or future directions in PCFT research?
There are quite a few exciting directions. One is extending all this to multimodality models, handling text, images, audio, video continually. How do you manage knowledge across different data types?
Yeah, that sounds complex.
Definitely. Another area is model merging. Instead of one model learning everything, maybe you train specialized expert models using PET, and then find clever ways to merge their knowledge together, maybe dynamically, as new tasks arrive. Techniques like ties merging or DARE are relevant here.
Combining the best bits of multiple models.
Potentially. Then there's moving beyond simple classification. How do we get models to continually learn more complex reasoning tasks? Visual question answering, decision making. These require accumulating different kinds of abilities over time, not just new labels.
That feels like a significant step up in difficulty.
It absolutely is. And finally, there's a big push towards more realistic and practical settings. Thinking about limited compute budgets, truly online learning from data streams, and crucially, task-agnostic or even unsupervised continual learning, where the model doesn't get explicit task boundaries or labels. How does it figure out what's new and how to learn it without supervision?
That unsupervised aspect sounds like the ultimate goal, almost. Okay, let's try to wrap this up for our listener, for the learner. What's the big takeaway here?
I think the big takeaway is that AI is actively moving away from static, monolithic models towards systems that are designed really from the ground up to learn and adapt continuously. Much more like biological learning in a way.
And this combination of parameter-efficient fine-tuning and continual learning, this PCFT, it's not just theoretical. It's the practical toolkit making that future possible.
Exactly. It's making advanced, adaptable AI more sustainable, more accessible, and ultimately more capable of dealing with the messy, dynamic, real world.
Think about it. AI that gets smarter over time without needing a complete reboot. AI that can run on your phone or local device, not just in the cloud. AI that might learn connections between language and vision continually.
And the sheer variety of these PCFT techniques, adapters, LoRa, prompts, selective tuning, shows just how much innovation is being poured into this. Each offers a different balance point.
A trade-off between, say, raw performance on the latest task versus how well it remembers the past versus how many parameters it needs.
Right. There's no single best method yet. It depends on the specific application and constraints.
So for people interested in AI development and research, this implies the tools and techniques are becoming much more sophisticated, much more dynamic.
Definitely. The AI systems you interact with in the future are likely to be in a constant state of learning and refinement, hopefully without those massive retraining cycles we see now.
Which brings us to a final thought, a technical question to ponder. As these models become truly capable of lifelong learning, what does that mean for the underlying architectures? Do we need fundamentally different network designs? How do we manage potentially conciting knowledge learned over long periods? What are the limits of stability and plasticity in these artificial systems?
Great questions. The push towards more brain-inspired or modular architectures might become even more relevant. It's a fascinating technical frontier.
Absolutely. Well, keep exploring that technical landscape. Thanks for diving deep with us once again on Neural Intel.